So welcome everyone to the last talk of today's session. And the speaker will be Alina Bucur from the University of California, San Diego. And she will tell us about L functions in arithmetic statistics.
Thank you, guys. And I know everybody has been doing this, but I want to add my thanks to the organizers who have made this possible, despite all the challenges. We really appreciate it. And, you know, to everybody who contributed to that book right there. Okay. So this might look a little, it might look high tech, but it's going to go low tech in a minute. I am going to try to basically channel Ser's attitude from the interview, which was we pick a narrative and we tell the story, and I only do what I like. So there we go. That's the principle today. So we are going to be talking about L functions in arithmetic statistics. I was given the task of talking about arithmetic statistics, and you know, everything that Ser has done every way that Ser has influenced it, and that's an impossible task. We need like months and months and months to just enumerate. So I chose L functions in arithmetic statistics, and I chose this question of you fix a finite field with Q elements, obviously Q is a prime power, and the smooth projective curve defined over FQ of genus G. So the question that we are going to focus on today is what can we say about the number of points or FQ points on this curve as we vary either the curve or the base field FQ. So of course the story actually sort of predates all of us, because you couldn't really do anything if you didn't have the Weil conjectures and the zeta function of the curves, which Weil proved for us, namely the fact that you can associate to this curve with zeta function, which has a very simple, since it's a curve, it has a very simple denominator, this dude over here. And then 1 minus u times 1 minus qu, if the curve is defined over FQ. And the numerator is a polynomial in u. So if you, of degree exactly twice the genus of the curve. The roots of this polynomial are all going to have absolute value q to the minus a half, which is the equivalent of the Riemann hypothesis in this setting. So this all comes from, of course, let's write it in green. This is all Weil. And the Weil conjectures, which of course Weil himself proved in the case of curves. The number of points on the curve FQ you can sort of recover from the zeta function, and it also has a it has a connection to the eigenvalues of the Frobenius associated to this curve. So it's q plus 1 minus the trace of Frobenius. And the other connection that exists between this Frobenius operator and the zeta function itself is that its eigenvalues are the reciprocals of the zeros of zeta. So this is why somehow, for some reason, this is cut off on my screen. I don't know about your screen. So I'm going to try to pull it up as much as I can when I get to the bottom of the page. Okay. So our question is, what can we say about the number of points on the curve as we vary things? But that, of course, translates into a question about the trace of Frobenius, or possibly even a question of the eigenvalues of Frobenius. If we feel extremely ambitious, we might talk about the zeta, the zeros of the zeta function of the curve. Okay. So today we are going to look at the distribution of the number of points, FQ points on a curve C as we vary different things. But I should say that the book itself, in the book, right, the main question that's of interest is looking at NQ of G, which is the supremum of this number, where you vary C over curves of genus G defined over FQ. So somehow, if you think about the distribution, right, if I have some sort of distribution, I don't know, some distribution function of the number of points, like the book is concerned with what happens over here. While today I'm going to focus actually about the distribution itself, on the distribution itself. And we are going to have three main directions that we are going to talk about. Namely, I call them geometric, probabilistic, and arithmetic, and you'll see what I mean in a moment. So the first one, the geometric direction, is where you fix the genus G and you look over the curves of genus G defined over FQ, and you let Q go to infinity. So this is, I call this geometric because basically you start with this with a curve scheme, whatever it is, defined over FQ, and then you start base changing to larger and larger fields. Then you have the probabilistic world, which is somehow the polar opposite of this, where you fix your Q, your field of definition, and you let the genus go to infinity. And I call this probabilistic because basically the results in that area, most of them look like the number of points over on C over FQ points of C is going to be distributed like a sum of IID random variables. So we're gonna see that in a moment. And the arithmetic direction is the one that I would very much like to focus on, and in a way, you can argue that it's somehow the richest because this one somehow connects the world of number fields with the world of finite fields. So a typical question would be, here you take a curve over, defined say over Q or some number field, and you can imagine how this changes for number field, and you reduce mod primes P, and then you let P go to infinity. So for those who work in the business, basically that means you look at the Sato-Tate conjecture. So we'll get there. And I like, this is the one that I will focus on. So I'm gonna go really relatively quickly over the first two and try to focus more on the third. Okay. So before I start, I have to explain how this all starts with a work of Serre, namely his book on abelian L-adic representations and elliptic curves. This was extremely influential. It's, I believe, the first edition, or possibly the notes that the first edition was based on, I couldn't really sort that out, dates to 1968 at the latest. I found a copy of it. There is there is a second edition that appeared much later, but the first edition dates from the 60s. And really, I'm not even going to talk about the whole book. The thing that the thing that sort of has influenced my life is the appendix A of chapter 1 in here. So this appendix is an amazing piece of work because it brings, it looks at question of equidistribution, and it brings into play a formula from representation theory, namely the Peter-Weil formula, and makes explicit connection to L functions. So you will see when I actually talk about it, you will recognize some features that every single person in here has seen. Even if you have never seen this appendix, you have seen some of this stuff. Okay, so the great thing about this is that he greatly extended in this the range in which we know how to do these things to compact groups. So you will see in a moment the things that you already knew. So some of you will know more than one of them, but everybody will know at least one. So let's see what the setup is. We start with a compact group G, and we take a countable family in the space of conjugacy classes of G. And then we assume that we have some irreducible representation rho of G with character chi, and assume that you have some function that, somehow the fact that is called n, v should be very clear, like what will happen here and what n we are going to take. So it's a function with values in integers that are at least 2 from this sigma to the integers bigger than 2. And we assume that if you take the product over all these in sigma of 1 minus, I keep wanting to say norma v, nv to the minus s, you assume that this is absolutely convergent for real part of s bigger than 1, that it has meromorphic continuation to real part of s bigger than or equal to 1, and you also assume no zeros and no poles on the real part of s equal on the line at 1, except for a simple pole at s equal 1. And you also define an L function that's associated not just to rho, but also to this XV family, that again, you might recognize the shape of that. And we assume that, again, this product is absolutely convergent when real part of S is bigger than 1, has meromorphic continuation all the way to the line real S is equal to 1. No zeros and no poles on that line, except possibly at S equal 1. So pretty much any L function you can think of fits into this description, right? And of course, if I take, you can, if I like somehow, this is exactly the setup that you have, say, for a prime number theorem, where the group has exactly one element. And also versions of this where G was finite would sort of give you the Artin L functions, or the Chebotarev density theorem. So under this condition, what Ser proves in this appendix is that the numbers of V's with n of V up to x is about x over log x. And he also gets a formula for the sum over V's with the nv up to x of the character chi evaluated at these classes that we've chosen. And that formula has a term x log x with a constant that is the order of the pole of the function, of the L function of the representation at s equal 1. So, right, this is going to be a positive integer if you have a pole, a negative integer if you have a 0, and if it has neither pole nor 0 there, is going to be 0. So, as you can expect. And then an error term, which is a little o of x log x. So we don't get a power saving, but we get something that goes to, that's much smaller than x over log x. And then you can use this is really a corollary of the first theorem, to get an equidistribution if you further assume that the set, that there is some constant such that the number of V's for which nv is given to is equal to a given value is always bounded by this constant. So in that case, you get equidistribution with respect to the normalized Haar measure on G, if and only if the L functions of the non-trivially reducible representation of G are holomorphic and non-zero at s equal 1. So basically that means that C of chi would be 0 for all irreducible non-trivial character sky. Okay, so this is the theorem, and I should say maybe a word about the general, the way he proves this is the way we prove this sort of any sort of equidistribution and any sort of asymptotic theorem to this day, and the way you've seen it done for the prime number theorem and so on, which is you have your L function, and basically you're taking L prime over L times x to the s ds. You integrate this somewhere where it converges, and because we made all our L's convergent for real part of s bigger than 1, we can go on the line real part of s is equal to 2, and then you move the line of integration to the left and get a bunch of poles. And that's so apply the Wiener-Ihara theorem, version of the Tauberian theorem. So that's how it goes in that appendix. And that is basically the, right, so you start here and you move and you find some residues. Okay. So what does this bias? Well, let me tell you that it biases quite a lot. So in the geometric situation, the goal here is to look at the distribution of the number of points on a curve C over FQ points of a curve C that's defined over FQ as genus G, where we fix the genus and we let Q go to infinity. So this is, right, fix G, let Q go to infinity. And the paper of Birch, I'm not going to explain because it was explained in the first talk today. Van de Heer talked about it, and I completely butchered the poor man's name, but that's the best I can do with Dutch names. Sorry. And then in 1980, Deligne uses that appendix in his V2 paper to get the equidistribution results that he uses to prove the V conjectures. There is also a paper of Serre in 1997, which he talks about the asymptotic distribution of the eigenvalues of a Hecke operator, TP, that basically also uses that and gets some super nice results. And somehow the full realization of this point of view appears in the Katz-Sarnak book in 1998. Right, so what Katz and Sarnak did, they started. You start with Deligne's equidistribution theorem from V2, and this tells you that if you look at hyperelliptic curves, over FQ of genus G, and you base change, you consider these curves over FQ and then FQ squared and FQ cubed and so on. Then as you increase this, the distribution of really zeros of the zeta function approaches the distribution of eigenvalues of random matrices in USP 2G. And then Katz-Sarnak show that in a certain sense, hyperelliptic curves are generic in the moduli space of genus G curves. So that gives you that the zeta zeros of curves of genus G in the large Q limit approaches the distribution of eigenvalues of random matrices in USP 2G. So it's the same group. But of course, they went much further and they gave us a philosophy that says the distribution of eigenvalues of Frobenius for some family of curves in the large Q limit will always approach the distribution of the eigenvalues of some ensemble of random matrices. And this ensemble of random matrices, I can use colors. This guy is dictated by the monodromy group of the family. And a lot of mathematics has sprung from this. The notion of family is a little bit mysterious, and I know we have a talk on Friday, I believe, about families of curves. So hopefully we'll find out some more about the best knowledge in the area, because I know that Peter Sarnak has been thinking for years about what is a family, what is a good family that you can sort of apply this principle to. Okay. So now let's move on to the probabilistic situation. So here the goal is to look at the distribution of the number of points on the curve where right, so this is the fix Q and let the genus go to infinity. And you have to really squint at this because my Q and my G are not that different. But right, so somehow for me, the story here, I'm going to start highlighting it starting in 2009. And I have to apologize because in all of this, right, this is all arithmetic statistics. The field started with Gauss. It's not like I'm going to cover it in 45 minutes, even if all I did was read the names of everybody who's worked it. So I decided not to filibuster and just choose something. So apologies to everybody that I leave out because of pitiless cutting of the history down to 45 minutes. Okay, so we have in here, we have this idea of looking at covers of P1 where you have some group that acts on the fiber. So this is Z mod LZ covers, the first one, where for L equal to Kullberg and Rudnick computed what happened to the number of points in this situation in 2009. And you know, this is very much like this L equal to means hyperelliptic. So in a way, we looked at exactly the family that gave Katz and Sarnak their inspiration. So we always start with hyperelliptic is the moral of the story. Okay, and then you can do for L prime, there is a series of free papers that I listed here that looked at this problem in various ways. The last one is the one that actually gives the result for the whole moduli space in this situation. And I should say that, like, I should make clear why I call this a probabilistic situation, basically because the number of points on a curve C, as this increases, right, as G goes to infinity, is going to approach here a sum of exactly Q plus 1, which is the number of points on P1 over FQ, IID random variables, independent identically distributed random variables. And they take the values. So in this case, they are Z mod LZ covers. So that means that in each fiber above a point of P1, I'm going to have either 0 points, 1 point, or L points. So these are the possible values. And this one is the least probable, L minus 1 divided by Q plus L minus 1. Then 0 occurs with probability L minus 1 Q divided by L times Q plus L minus 1. And then this one has the rest, which is Q divided by L, Q plus L minus 1. So those are the three possibilities. And now you see why this is probabilistic, because every single time what you're trying to do is you're trying to find some, you're trying to model this using some sum of random variables, and the idea, the hard part here is the independence as you go higher and higher. Okay, and I should mention there are there are other papers, but the ones that I want to highlight are the S-free curves proved by Melanie Wood in 2012, because this brings in some of the results of what I call Bargavology into the picture. And then there is the biquadratic case that was done by Elisa and Meleleo Milione in 2017. Another thing that has a very different flavor is you can, in 2004, Björn Poonen wrote a paper about Bertini theorems over finite fields, I think it was called. And using that idea that arithmetic sieve that is very different from arithmetic, I should say geometric sieve, that is very different from the sieves that we had before. Like anybody who does analytic number theory and might know those sieves, this is quite different in flavor. And from that you can get plane curves, complete intersections, and I should say that this was me. Oops, David. And Lalin. The problem is that they are alphabetized by first name in my head somehow. Complete intersection, that's me and Kiran, and I do not remember any of the years. And then a generalization of that was done by Ehrman and Wood in 2012, where they did semi-ample Bertini that basically sort of has a different story in the sense that they look at a situation where the fibers are independent. What happens in two fibers are independent phenomena, but you can have some dependence inside the fiber. So that pushed it further. So I wanted to mention all of this because this is a story where you have methods from all over the place coming into play. Okay, another method that comes into play, something that comes from topology, namely cohomological stability. So somehow the ultimate reference is this paper by Ellenberg and Venkatesh and Westerland from 2016. And this cohomological stability was used by Achter, Ehrman, Kedlaya, Wood, and Zurich Brown in 2018. And whenever you see that many authors, you know it's a paper from AIM, to look at the number of points on a curve where C just varies over mg, the whole moduli space of curves of genus G as G goes to infinity. And what they get is a Poisson distribution. So this is conjectural based, like assuming certain things about cohomological stability holds, namely that cohomological stability kicks in early enough for this to work. Poisson distribution with mean Q plus 1 over Q minus 1. And I should say that this is a conjecture. Okay, so I should say that when the Ellenberg Venkatesh Westerland paper deals with Hurwitz spaces. These guys look at the full MG, and of course we have no idea how to approach any question like that, just except like if we assume a bunch of things. Nobody can write a random curve in MG. Okay, and I should mention that very much in the spirit of the book, which looks at this maximum of the number of points over a curve of genus G over FQ, is the Drinfeld-Vladutz bound from 1983. And I had to do that because, you know, there aren't that many people on this call who can pronounce Vladutz. So let me tell you, I can do Romanian names, not so much Dutch. So they prove that the lim sup of this extremal number of points divided by the genus of the curve is at most square root of Q minus 1. What you get from the usual bound is 2 times square root of Q. So that would be what comes from sort of cohomology, if you want. But this is much stronger. and uses, again, completely different method from everything I explained before. Okay. And now we get to my favorite part, which is the arithmetic situation. So remember, this is the situation where you reduce, you take a curve over Q, you reduce it mod P and let P go to infinity. And the great thing about this is that, right, this curve has an L function, and this is, well, more or less the product like this. So I'm right, P should have good reduction and things like this for what I'm going to write later. You can make sense of it even without. But these LPs are basically the L function, the L functions of
Alina,
those curves.
Sorry to interrupt you. There was a question by Felipe Boloch in the chat.
Oh, I'm sorry. I have not seen the. Somehow my chat disappeared. Go ahead.
Oh, yeah.
If there is data, I don't know. I'm hoping that either Jeff or Kiran is here and can tell me, because I have no clue. If right, is the conjecture, you're talking about the conjecture about the number of points over mg, right? The one from, yeah. So that one, the short answer is I don't know, but Jeff is there and he's going to tell us.
The whole point is that we can't get data because we don't know how to write down curves in big genus. So what we can show is that if Q gets big faster than G does in the right way, then sure, but we can't actually harness reasonable data in for big genus because we can't write down the curves.
Great. See, I'm doing my job. We are supposed to harness the collective knowledge of the community. Excellent. So for this arithmetic situation, the magic words here are Sato-Tate conjecture. So this was formulated in the 60s. There's been some work done in the 70s by Yoshida, where he proved it over function fields. And then there is this Lang-Trotter paper where they formulate their conjecture, and that generates interest in refining the error terms in the Sato-Tate conjecture. And this was Kumar Murthy in 1985. He actually writes a paper about what can you say about Lang-Trotter under GRH. Assume GRH about every L function in sight. What can you say? And the answer is, well, not all that much, because somehow Lang-Trotter is too fine a conjecture to sort of attack it on average like we do with L functions. We can do with L functions. A nice piece of history that I found out when I was preparing this talk is that the first numerical results for Lang-Trotter that they actually cite in their paper were done by somebody in the USSR at the time called Tushkina. I assume is a woman given the name, but I don't know. So the takeaway is that the first numerical simulations of Lang-Trotter were done on Soviet computers, which I find interesting, to say the least. Okay, so in 1994, in this conference on motives, Serre gave the definitive formulation of the Sato-Tate conjectures in terms of motivic L functions. As even formulating the Sato-Tate in the 60s, it was originally formulated for elliptic curves, and maybe even elliptic curves over Q at first, and then extended and so on. And the 1994 paper by Serre gives the ultimate formulation in terms of motives. And then in 2010, Fiteke, Kedlaya, Roger, and Sutherland, they formulate the Sato-Tate conjecture for genus 2 curves. And maybe I should sort of give you an idea about sort of the order of difficulty of formulating these things. So for genus 1, you get three possible distributions. One is for non-CM curves, non-CM elliptic curves, because genus 1 we're talking about elliptic curves. And then there are 2 for CM, either over the field of definition or CM over an extension, a quadratic extension of the field of definition. So those are the 3 possible distributions, and the Sato-Tate groups for this would be, right, this is SU2, this is SO2, and this is the normalizer of SU2 inside of SU2. So there are only 3 cases. For genus 2, I'm sure Drew or Kiran will correct me if I got this wrong. I think there are 52 total distributions over number fields in general, and 34 for curves over Q. And the genus 3, they are working on it. I know that, right, Kiran and Drew and Francesca are meeting every week to sort out this. And I don't know how many hundreds are we up at. 410. Ooh. As you can imagine, I'm not going to list the 52 or the 410. Okay, go see that paper. So this is some combination of these 4 guys and subsets of these 4 guys. Okay. So I should mention then the Sato-Tate conjecture for elliptic curves has been proven in, like I always think of these 2 papers as being the ones that, that if you put together, you get the full proof of this. And the heart of the proof is you use Serre's method that from that famous appendix to reduce the problem to proving meromorphic continuation plus correct analytic properties on the famous line at real part of S equal 1. For the L functions of all the symmetric powers of the elliptic curve that you're interested in. And this one, the way you approach this to prove the meromorphic continuation and so forth is via potential automorphy, which is basically the only thing that we know how to do. So this proves it for the case of E non-CM defined over F, which is either totally real. So I think the original papers maybe did it only over Q, but it's been extended either totally real or a CM field. And what they prove, right? So the L function of the elliptic curve, if we normalize it sort of Serre's way, is more or less equal to a product of 1 minus AP p to the 1/2 minus s plus p to the 1 minus 2s to the minus 1. And you know that these APs take values in -2, 2. And then the Sato-Tate conjecture, because I should at least tell you what the Sato-Tate conjecture is, since I've been talking about it for a few minutes now, is that if you look at the number of APs in an interval I, sub-interval of, well, you can really take, it's enough to take it for 0, 2 because it has a symmetry, but so P of good reduction and, well, P less than X. Of course, I should say norm of P and so on, but I cannot, if I write by hand, I cannot possibly write the funky P's. So we are going to stick with normal P's here. And this should be the Sato-Tate measure of the interval I times X over log X. And the Sato-Tate measure is 2 over pi integral over I of sine square theta d theta. That's what it goes out. So that's the Sato-Tate conjecture. just so everybody knows what I'm talking about. Great. So this has sort of got Kiran and me interested, and in 2010 we actually looked at a question that Ser had looked at, and it's in his collected works. And it starts with the fact that, right, Faltings in the 80s prove that if you have two non-isogenous non-CM elliptic curves over some number field, then there will be some some finite place of that field K, such that both curves have good reduction at it, and the AP coefficients are different. So in other words, he proved that, right, the L functions will be different. This is what this boils down to. But it's more than the L function will be different. Like sort of two of the APs will be different. And we wanted to find a bound for like how far do you need to look at to be guaranteed that if you have two non-isogenous curves, you are going to find such a P at which the traces of Frobenius are different for the two curves. And so for this, we used an effective Sato-Tate. And by effective, I mean under GRH for a whole lot of functions that would be dictated by Ser's approach, which functions you should look at, and you should assume GRH. And you assume GRH, right? When I say effective, is the same type of effective that you would like to sort of do for the prime number theorem. What we can prove is that pi of x is about x over is asymptotic to x over log x. But what we would like is an error term with a power saving in there. That's what makes it effective. So this is what, by effective Sato-Tate, I mean you have something like this plus a big O of something with a smaller power of x in it. Okay, so that's effective. And then in that case, you can prove that, right? So actually sort of Ser gave us the roadmap to go to how to do this in his collected work. So in general, you prove a bound of this form, log n squared times log n to some power, where n is the product of the conductors of the two curves. And the name of the game is to make this b to be 0. So what Kiran and I managed to prove, I think it was b equal 2 in 2010. And then Ser kindly pointed out that one can use, he had also worked on this, and he had gotten a B, if I remember correctly, it was 6, but using mod L representations, he pointed out that you can use Eladig representations and run his proof, and then you would actually get all the way to the famous B equals 0. And so we hadn't done that in the 2010 paper. However, we went back to it a little bit later, and in a paper with Francesc Fité and Kiran Kedlaya that is still to appear because it's submitted somewhere, I forget where, but it's on archive. So we generalized this to the case of a billion varieties, not just elliptic curves. And there our generalization gets all the way to b equals 0. And I will close with mentioning that, again, this is all under GRH. Everything is under GRH. For every function, L function that you see, you assume GRH. So this also has a funny little application that it's much more in the spirit of the book. So I wanted to mention it. You can look for, like, if you have a CM elliptic curve over some number field K, you can look at the number of primes less than X such that AP is as big as possible, which in this case would be the floor of 2 times the norm of P, right? You cannot get any bigger than that. And Ser conjectured that this number would be about 4 over the asymptotic for this number as x grows is 4 over 3 pi times x to the 3/4 divided by log x. So in this paper that I mentioned a moment ago, under GRH, we managed to prove that at least R of x is a VAT size. But and then we discovered, to our delight, that actually VAT was an unconditional result that was proved a few years earlier in 2017 by James and Pollack. So the unconditional, they proved the thing that Serre had conjectured. And I apologize that I do not know when Serre conjectured that. So I actually, before I end, I have 2 questions for essentially for the for all of you. And I was hoping to actually ask Serre this, but apparently he's not here. So one is, when did he make this conjecture? And 2, from the 3 points of view that I talked about, as you've seen, he has influenced tremendously the geometric point of view and the arithmetic point of view, but I couldn't find so many contributions to the probabilistic point of view, which means I must not know about them because I cannot believe that they don't exist. So homework for everybody, put in Zulip whatever you know about that. Okay, I'll end here with homework.
Okay, thank you, Alina. So are there any questions for Alina?
Any answers?
Well, I can tell you that this is conjectured both in the book that we are celebrating, but also in the lectures on NXP of 2012.
Okay. Okay, so I will put.
Yeah, that's an upper bound.
Yeah.
So I wanted to ask you, in this arithmetic situation that you have some object defined over a number field, are there problems that we cannot tackle within the scope of the Langlands program, that is using L functions that we know that will have the desired analytic properties?
Well, it depends what you mean by tackle. So for instance, this one where say that you're looking at this problem of finding a bound for this P where the traces are different. The actual expectation is actually something on the order of log n, but L functions will never get you that close. L functions, the best you can hope for is log square of n. And this is a little bit like, the smallest quadratic residue. The L functions can give you a result, but you expect what you know and sort of expect to be true is a much better result than that. So if by tackle you mean say something, I'm not sure, but if you mean actually get to prove an actual asymptotic formula for this and so, or a tight bound, then I would say yes.
I was also thinking in Klosterman sums where maybe we don't know where these L functions come from, but
yeah, no, I mean this was just an example. Come on, there is a whole world out there that can fit in this category. This was just an example, just from 5 minutes ago. That's all.
There is Elisa that wants to ask you a question. Please, Elisa, go ahead.
Thank you. First of all, thank you, Alina. I really enjoyed the talk. It was a very nice one. And I have a question about your last slide, because actually, I remember I think it was 2 years ago that you talked about this result in AGCT. And
yeah.
When you got the result, I was trying to use it to prove that you can prove that there are infinitely many curves that has the maximum number of points. And it doesn't work, right? It's not the...
Yeah, so what happens, the reason why we do this for CM elliptic curves is that if you look at the Sato-Tate distribution, right, if it's a non-CM, it looks like this. So at the extremal point, it goes down. So it's impossible. You cannot make up for that. It just goes down so fast that you cannot do anything to like sort of capture how close it is with this method at least. But for CM, it looks like this. So the measure gets bigger and bigger over here. So you have a chance. So this is what is hiding behind our result. So I don't know of something that would get you what you're trying to do. Maybe somebody else over here knows. I don't. So did you guys make progress on proving infinitely many curves?
No.
Because that would be super cool if anybody proves something like that.
Yeah, of course.
Okay, I'll add it to the list of things that I should talk about on Thursday about perspective.
And then I had another question now that I can speak. So, I mean, I didn't know this result, and it's quite nice that you mentioned that somehow hyperelliptic curves behave like generically in the Fourier space of genus G curves. But I mean, I guess that this result is, maybe you said it, but I didn't get it, when the genus goes to infinity, right?
Yeah, no, this is when Q goes to infinity, about things being generic. This is the Katz-Sarnak world.
When Q goes to infinity. Okay, because I mean, well, maybe you, Christoph.
So you fix the genus G and you let the Q go to infinity. You look over larger and larger fields and you take the large Q limit. That's when they are generic.
Because for genus 3, I think that Christoph, you had this paper with other people and you get like some skew distribution, so they are not symmetric. But I mean, maybe you do it with a small.
Yeah, but I mean, yeah, you know, I mean, the things that we observed, like it's completely heuristic, that somehow you have more curves with many points than curves with very few points, and that gives you like something which is not symmetric. But this is when, I mean, you can't spot this distribution. I mean, you can't spot this difference on the distribution because it is like a lower order term. I mean, the difference between the two. So
presumably,
like a refinement of the distribution.
Yeah, so presumably you can recover this a little bit. So the way Katz and Sarnak do this, right, is that they look at this. So at every finite level, you do, like if you look over FQ to the n, for instance, right? If you base change to FQ to the n, then you don't get this distribution of eigenvalues of random matrices. You get that plus an error term. So they write all these lower order terms would be in that error term. And the point is that when you really let Q go to infinity, that error term goes to 0. So at no finite level is it true that it's really the symmetric distribution. But when you take the large limit, it moves that out. So what Christoph is looking at is sort of before the smoothing takes place. So that's, yeah, is the lower order terms.
Yeah, okay. Thanks, Alina. Are there any other questions? Well, if not, thank you again, Alina.
Thank you guys again for organizing this and for asking me to speak too. Let me stop the share.
And yeah, well, I think that's the end of today's session, but let me pass to the organizers in case they want to make some an announcement about tomorrow.
No, unfortunately, no excursion in the Kalong tomorrow. So. Yeah. Yeah, thanks, Alina. I mean, it was perfect. Exactly what we had in mind. Great talk. And I'm looking forward to see the open questions tomorrow.
Well, I have to write it first.
Oh, on Thursday.
Oh, the open questions of other people because I'm not speaking tomorrow. Sorry. Okay.
No, it's also cool that you presented all these results for, I mean, all these asymptotic results with the Poisson distribution and all this. I mean, these are quite, it's also strange because it seems that, I mean, the Poisson distribution says that you should expect like a mean which is a bit higher than Q+1, which would be like the medium term somehow. You obtain Q+1 plus 1 over Q-1.
Yeah, it's slightly bigger than that. Yes, that is something funny, and that's actually something that it was super funny when we sort of look. There are these things that you can look at, like in the Ehrman Wood paper, you get like this. Not just like you actually can prove some theorems for certain families where you get this number of points slightly bigger. And in the complete intersections one that I wrote with Kiran, when the number of points is actually slightly less than Q+1. So it was really interesting to sort of get this conjecture and sort of see who we expect to win, the guys with more points and the guys with fewer points. So you can think of this as good news for you because you want things with more points.
It would mean that the problem to find curves with very, very few points is more complicated somehow. So we are lucky. All right.
Okay.
Time for bed then.
Yeah.
Time for the